solutions written up and posted. But I did realize I forgot to bring, still from forgetting to bring I wanted to show you a histogram of the results of the last exam. I apologize. I only remembered it on the stairs on the way up. Anyway, any other questions about anything? Yeah. I'll take it under advisement. No white chalk. So we were solving the, hello. We were solving the problem of not an infinite well, but a finite well. Okay? And let me just quickly write down what we did last time. We have these three regions, and this is the potential. But on this, or it's an energy diagram. That, of course, is x. And then we had an energy. Move the 2. We have an energy less than U0, where U0 is the value of the potential out there. When you solve these problems, you can get to where you can just do much of this math pretty quickly. Although don't try to skip steps until you've done this enough where it is quick, right? But here, where the potential is 0, the solutions in region 2 are A cosine kx plus B sine kx, where k equals the square root of 2m e over h bar squared. And I just write that down because I've solved it so many times. And of course I did it last time, but you should almost be able just to write that down, okay? If you get to where you can write this down, not because you just sort of memorized it or something, but because it's straightforward math, right? And you've done it enough times that you can pretty much write it down, or not just write it down, but solve it, but really quickly with confidence, then you're going to be okay shaped for the exam, okay? Last time I taught this class, I sort of thought everyone just could write this down because they've been watching me do it. Osmosis doesn't work, right? Just practice it. It's easy algebra. When I gave exam last year, though, if you weren't just good at writing this stuff down, people just had a wipeout on the couple problems where you had to do this, all right? So you should just be able to do that. I mean, there's always some guessing as to how to deal with the boundary conditions. It's a bit more subtle, but just the fact that cosine is going to solve Schrodinger's equation, and that's the k you're going to get, you should be good at that, all right? In 1 and in 3, the energy is less than U0, and so we got solutions psi 1, let me call it C, and it was e to the alpha x, where alpha was the square root of 2m, and here it was U0 minus e, the positive quantity, over h bar squared. And in region 3, I have d e to the minus alpha x, and that's allowed, right? So it was a and b for cosine and sine, and then I allowed e to the alpha x, which for x less than 0 is going to decay to 0, is over here, and e to the minus alpha x, which for x greater than 0 is going to decay to 0 over on the right. Now I need the boundary conditions. I mean, in the sense I've already imposed two boundary conditions, the x of infinity, infinity, and minus infinity. But the other boundary conditions are at 0 and L. Now last time I argued, or not last time, last week, I argued that that momentum was like d psi dx, and that if psi was discontinuous, then if psi is not continuous, d psi dx goes to infinity, therefore p goes to infinity. This is not allowed. Okay? Now I need to make another argument. The kinetic energy, well, it is equal to p squared over 2m. And so in quantum mechanics, that turns into d psi squared dx squared with some constants, right? Or in other words, d by dx of d psi dx. Okay, just, right, straightforwardly. And that's going to give me the kinetic energy. All right, so because kinetic energy is momentum squared, it's two derivatives of psi. So if d psi dx is not continuous, the kinetic energy, well, then d by dx of d psi dx will go to infinity, right? If something is not continuous, and then I look at the derivative, that abrupt change means an infinitely fast change in the derivative, an infinitely large derivative, right? And I went through that in detail using the definition of derivative, all right, as a, you know, as the limiting process from the basic definition of derivative. And so that would imply that kinetic energy is going to infinity. Okay, so d psi dx must be continuous. So all of what I've just discussed is basically to say a new condition. We had this before. Psi, here I put it in terms of negative. Psi cannot be not continuous. Therefore, psi has to be continuous, right? Secondly, this derivative of psi has to be continuous, right? And just to remind you, what do we mean by first and second derivatives like that? Right? So here is like, here's a parabola. This is psi versus x. If that's a parabola, psi prime, and this is just an increasing slope. The slope is negative but increasing, so psi prime is that. And psi double prime, in this case, is some number greater than 0. Right? Straightforward. I mean, I could have done some other shape, and if this was continuous, and the first derivative was continuous, and therefore the second derivative was well behaved. A counterexample would be, say I had like this. Here's psi. Psi is continuous, right? But it was something that was curved up. And so this had a slope. Let me see if these were both pieces of a parabola. That would simply be a slope that was like that. But here suddenly the slope's the other way. Okay, so that's psi. Oh, and I'm sorry. I'm using a definition here which I may not have formally introduced, but it's convenient. Prime. Everyone happy with that? Saves you from writing d by dx. It's analogous to writing dot for time derivative. Prime will mean a space derivative, or in fact, sort of a derivative with respect to whatever variable you're talking about. Dot is kind of reserved for time. Prime is usually for x. Okay, so this is psi prime. What the heck am I talking about? I almost drew it right. See, this is something that's curving like that. The the slope is increasing and the slope is positive. Here the slope is negative, but possibly, well, if I draw it like that way, it's possibly increasing, but there's this huge discontinuity. So that kink leads to a discontinuity, and so then the second derivative is something that took an abrupt drop downwards. So this thing is a constant actually, but then it has then it goes off to minus infinity. If you will, this is a negative delta function, as I mentioned before, although that's not even mathematically well defined. It simply goes off to infinity. So this thing is nonsense. It goes to minus infinity. Okay? So that's the sort of thing that's not allowed. Yeah?
Does psi double prime recover then after the x equals 0 point to have some behavior beyond?
Yeah. I mean, if I drew this, let me see. I just draw these down. It's kind of hard to say what I did. Let's suppose I really drew a parabola here. You know, psi equals x squared, but with some offset. And here's just another one that's the exact same with some offset. Then it's just going to look like this. They're both slopes that are increasing. As I walk along, the slope is increasing. But it jumps from a positive slope region to a negative slope region right abruptly right there. Right here where this is 0 is the place where this would cross 0. So I actually drew that about right. And if I drew these with the same curvature, these would be the same value, but this discontinuity is just is an infinity. Okay? And so really it's just a simple point. That's an inflection point. Or no, that's not that's a kink. That's a kink. And the second derivative goes berserk. Now, you might have noticed something. When we did the particle in the infinite square well, the so-called particle in a box, we didn't use this requirement, okay? And in fact, we didn't honor this requirement, okay? Which is why I didn't mention it already. We had actually the lowest state was just square root of 2 over L sine n pi over Lx, right? And that was within this region, and outside psi was 0. So right, blowing that up, this looked like that there, okay? Which is a version of that bad thing, okay? The reason it was allowed here, and I don't want to justify it fully, but you can see it. The reason it's allowed is because the potential was infinity. The potential had gone off to infinity, which was suppressing psi like 1 over infinity, if you will. Okay, I mean, psi was utterly 0 here. And so the fact that I had a discontinuity in the second derivative, well, I don't know. I mean, I guess the argument is the particle ran into an infinite hard edge, okay? But don't worry about it. If I have a potential which has an infinity in it, i.e. the infinitely deep particle in a box, or there's a classic problem which it's even in the book. It's not crazy hard. I don't think I'm going to assign it or put it in an exam, but you can make the potential is just a delta function at the origin. If you have sort of mathematically subtle things like that, some of these rules are a little bit, hard to apply. Let me just simply tell you that in any problem except with the infinite potentials, both of these rules I've just developed, that I have to have the whole thing with no kinks, such that this derivative and and its derivative are continuous. It simply applies. And it applies to any real physical problem, okay? Any real physical problem, it applies. Particle in a box is not a real physical problem. Infinite potential is not allowed. In fact, this is the better version of the particle in a box. So let me just continue with it. Right, that's the real physical version. I could take U0 to be quite large here. And in fact, if you're really unhappy with the fact that I didn't apply the psi prime being continuous boundary condition, we should solve the problem this way. Mathematically, that's well defined. And then just take U0, go into infinity, take the limit. We'll recover the particle in a box solutions. I mean, it would be a lot of work. But maybe that would make you happier mathematically. Although I don't get fussed about these mathematical niceties when I can help it. All right? Fine. So we have psi, continuous, and we have psi prime. continuous. I think I want to erase the board a little better. And our visitations continue. All right. So, at x equals 0, we're basically saying psi 1 at 0 equals psi 2 at 0, right? So psi 1, I'll write it out this first time. Okay, so that's c e to the alpha times 0 equals a cosine of 0 plus b sine of 0, okay? And that's 0, right? And e to the 0 is 1, so c equals a. I already have an answer for one of the terms. I have psi prime at x equals 0. All right. Taking the derivative, so I'll take the derivative of this. I get alpha c e to the alpha x. Alpha times c, and e to the alpha x at x equals 0 is 1, equals, okay, I have to take the derivative of this and then plug in x equals 0. All right, so that's, let me see, it's a times minus k sine of kx plus b times k cosine of kx, all evaluated at x equals 0. When I put x equals 0 into the sine, that goes away. Sine of 0 is 0, but in the cosine of 0 is 1. So that's plus equals bk. So I have alpha c equals bk. Okay? So those were easy. And since c equals a, I also have that alpha a equals bk. That's just combining this fact and that fact. Okay? At x equals L, psi is continuous. Okay, that's a little messier. Again, that's to say psi 2 at L equals psi 3 at L. So that's to say A cosine KL plus B sine KL equals D e to the minus alpha L, right? Is that fine? Now you just got to do this, right? And now psi prime is continuous. Okay? So I've got to take the derivative of psi 2. Actually, I did it up here, but I'm going to plug in for x equals L. So I have, there's a k overall. So it's k times minus a sine KL plus b cosine KL equals the derivative of psi 3. The derivative of psi 3 is minus alpha d e to the minus alpha x. Let me write it down here. Minus alpha d e to the minus alpha L. All right? So it's a bit messy. Let me stop at this point and do something that maybe I should have done at the beginning. Just ask, a simple question. How many equations, how many unknowns, right? If I'm going to be able to solve, I should have the same number of equations as unknowns. So let's look. I've got A, B, C, D, four unknowns. I do know the K and the alpha, right? And I had 4 boundary conditions. Okay, so I should be set. In fact, I'm a little bit puzzled because that's 4 boundary conditions, and I also have the overall normalization condition. So I think there's a little bit of redundancy, but that's fine. Would have been bad as if I had not enough boundary conditions. Okay. Let me see. I want to combine these two. So dE to the minus alpha L is that. Okay. Let me rewrite this a second. Happy with that? I just divided by minus alpha. So all of this is equal to this is equal to all of that. Plus which I'm going to go ahead and say B equals alpha over Ka, which simply came from these two simple equations. All right, so then in one fell swoop, I'm going to write A cosine kx plus for B, I write alpha over K times A sine K KL. So this is A times cosine KL plus alpha over K, which came from B, sine KL. That was equal to this term, which is equal to all of that, which is minus K over alpha. Oh, and there's an A again. I'm going to pull the A out. A times minus sine KL plus, and B is alpha over K cosine KL. This algebra is in the book. You know, you don't feel like you have to sit here and copy it down. But you should be able to solve a problem with this much algebra. I know it's tedious, but it's simple in a way. It's straightforward. You just got to do it. All right? And you need to be able to do this. So I'm simply going to combine terms with the cosines and the sines. Okay? Let's put the cosines on the right. I have cosine KL, which is this term. A canceled out. On the left, I had minus K over alpha times alpha over K cosine KL with a negative sign. So if I add it over here, I simply have 2 of the cosines. On the left, I have minus K over alpha with a minus sign and another minus sign. So I have plus K over alpha times sine of KL. That's this term. And then I had a positive term on the left, which I bring over to the right. So it becomes minus alpha over K times sine KL. All right? So 2 cosine over sine is cotangent, right? Which we don't often use, but there it is. Okay, that ugly transcendental solution, transcendental equation is as far as I can get. It's not an expression for A and B and C, but it's an expression that relates alpha and K. Okay? Oh, sorry, now I understand my mystery with the number of unknowns and number of equations. I had 4 unknowns, and I said I know K and alpha, but not quite, right? In the sense that, like the particle in a box, it turned out I couldn't pick any old energy. Okay? And here I started with these equations, and I've ended up with some relationship between K and alpha. And K and alpha have energy in them, right? K and alpha have energy in them. I mean, in fact, let me write it here. K over alpha Can you see from the definitions over there? This is simply going to be the square root of E over U0 minus E. Right? Because there was the 2m over h bar squared thing in the square root going along. So this is a relationship, this is an equation that has E in it. And just like the particle in the box, this is going to impose conditions on the energy. So to count up again, I had ostensibly 4 unknowns, A, B, C, D. I had 4 boundary conditions, but I also have the normalization condition. Remember, at the end of the day, I'm going to say that psi, the integral of psi over everything is going to be 1. So that's essentially a 5th thing. So I actually have 5 equations, and I have A, B, C, D, but essentially now I'm going to pose another condition on the energy, right? Even though in some sense I know what K and alpha are in terms of energy, the final boundary condition is a final condition. It's going to impose something on the energy. Now this gets a little mathematical. The book has a description of how this works out. I'm going to do a slightly simpler, although a little bit more hand-wavy description. And we're not going to try to do something too rigorous here. But I want to give you the flavor of the answer. Okay? I mean, this is exact, no problems. But let's just examine this thing. Let me just write it again. 2 cotangent, well, actually, let me even write it out. It's cosine of KL over sine of KL equals this beast, K over alpha minus alpha over K. I'm going to go ahead and write it in terms of, well, no, I'll write it this way. K over alpha minus alpha over K. But where K over alpha is, just writing down again what I had over there, U0 minus E. Let me make a comment. What is E over U0 minus E? And I started out, I said the energy is less than U0. This is less, well, no, fine, let me just leave it at that. Okay, so let's look at this side of the equation. If I plot K, which I don't know yet, cosine over sine, if this is 0, the sine is infinity. So this function starts out here. At some point it hits 0 where this thing is 0. And then it goes off to negative infinity. Okay? And this value where it hits 0, this value where it hits 0 is when KL equals pi over 2, right? So if this is K, this is the point KL equals pi over 2. So in other words, this is the point pi over 2L in K. And this is pi over L. Okay. And then what happens is you go a little bit bigger than pi over L for K. Both the cosine and the sine are negative. And it jumps back up to infinity again. And then it comes down. This is where KL is 3 pi over 2. It becomes negative here. Here it was negative because the numerator was you're up here in this quadrant of the circle. The numerator was positive, but cosine became negative, etc. And so this is 3 pi over L, 3/2 pi over L. This is 2 pi over L, etc. So this is what the left-hand side of the equation is doing. It's the set of curves, okay? And then the solution to this, right? I mean, you've probably seen this before, but maybe I need to remind you, if you have a transcendental equation like that, transcendental equation meant I can't get a simple expression for E out of this. Because by God, I've got a cosine, I've got a sine, and those are of the square root. And then over here, I've got this nasty combination of square roots. So what I do is I just punt, I plot the left side, I plot the right side, and I see where they overlap. Okay? And qualitatively, and I'm a little bit worried here because I'd worked out my notes twice, but now I see an error. So I'm going to do this without my notes. Let me see, k over alpha, this is bigger than that, but u is always bigger than e. So this is bigger than 1. But let me see. You can start at 0 energy, and this will be finite. And then as energy hits u naught, this will go off to infinity. So this is something that goes from 0 to infinity. And this is 1 over that. This thing is going from minus infinity to 0. So this is a bit of an ugly beast. But if k is 0, this starts at 0. This starts at minus infinity down here. It comes up. It comes up and then shoots up like this. Okay? And if you fully think this through, for different values of u0, what you get are curves like this. So this would be one value of u0, and this would be another value of u0, say u0 prime. I only want you to take one thing away from this. The sinusoids, this cosine and sine, gave these curves, which I think is understandable that it's a repeating set of curves for different values of k. And then the right-hand side are these curves, and the point is that there's intersections on this graph, and those are the solutions. Okay? So this was ugly algebraically, but that's what it is. And those points of intersection are the only values that are work. And so in other words, those are conditions on E, and they're quantized. Okay? So we recover the particle in a box behavior where there was only discrete values of energy allowed. But it's much, much more opaque exactly what's going on here in terms of what are those values of E. Okay? And something that I don't want to try to talk through because it's a fair amount of discussion, it's in the book, is that in fact you can show that even if u0 starts to go all the way to 0, there's always one point. This first line will go from minus infinity to infinity, and it's at least going to intersect that curve. I mean, you can kind of see it, but I don't want to really try to justify it. And then if u0 gets bigger, you can start to intersect more curves. What is this saying for the problem? Let me just erase all the scribbles and draw the wave functions down. There was always one solution. This is an interesting fact about these quantum mechanical systems. If you have a potential well, this is called the potential well. It's a box with finite height. It turns out there's always going to be a bound state, no matter how low u0 is, even if it's a tiny shallow well. This curve and that curve, this lower u0 is going to make this guy get steeper and steeper, but it's always going to cross this once. It was, well, the sine and the cosine aren't quite so obvious, but they do again form a psi that looks kind of like that. Okay? And then it is something that's, well, exaggerated a tad. Let's even draw a psi relative to 0 here. It'll be something like this, and then it's going to go to 0 out there. And the way mathematically I constructed it, I won't have a kink right there. That was my whole argument about the boundary conditions. I imposed those. I made the derivative equal. There is no kink. However, out here, it's the exponential fall off, and out there, it's the exponential fall off. And it's some like hump in the middle. And that's the lowest state. This would be some psi 1. And then there are higher states. that look just like the particle in a box, okay, etc. So this is the correct treatment, really, of a particle in a box if I take U0 going off to infinity. And you can show mathematically that the solutions turn into the particle in a box solutions, but they're obviously more complicated mathematically. I don't have a nice formula for the energy, but the qualitative features remain. An interesting quantum mechanical point, though. The wave function exists over here, okay? Over here is a place where, if you will, the kinetic energy is negative, imaginary. Or, well, sorry, the kinetic energy is negative, which means the momentum, if you will, is imaginary. Okay, mathematically, it turned to k in a cosine or sine or x e to the ikx into an alpha and an exponential without the I. Okay, and so the in ordinary mechanics, the particle is not allowed to be here. U0 is greater than E, and the kinetic energy is negative, which doesn't have any meaning classically. The particle's not, I mean, it spends most of its time in the center, but the wave function, if you will, it samples this forbidden region, okay? And there's a discussion in the book you can read, and I'll just sort of repeat it. That may seem like you're going to get into something that's really not allowed, in the sense of you can't really have a particle here. So what does it mean that the wave function is samples out there? This isn't a very large region, and if you try to actually construct a wave function that is localized there so that you're going to be guaranteed to have the particle there, then the Heisenberg uncertainty principle says, well, the momentum will start to get very uncertain, and the energy could then be big enough that you're no longer, it's actually bigger than U0, and you no longer are violating this sort of energy idea. That's sort of hand-waving, but it is accurate. We shouldn't get too upset about the fact that the wave function spills out. And it's an interesting feature of quantum mechanical systems, okay? And so this is just kind of what you would have expected. I said that if it was a particle in a box with an infinite well, I had this hump, which had a discontinuity in the derivative. The real better treatment with a finite potential, you know, has all this complexity, but avoids that. I have a little bit of a spillover. If you push the potential out to infinity, as you can see, alpha gets bigger and bigger and bigger, which basically means this little bit just gets steeper and steeper and steeper, shorter and shorter and shorter, and you smoothly go to the slightly artificial particle in a box, infinite square well initial result. Okay? So that is a particle in a finite well. All right, so let's jump to a new case. What would happen if the energy is greater than U0? In fact, let me just start on this same drawing. Let me erase these wave functions, but keep the drawing basically. Region 1, region 2, region 3. What if the energy is up here? What if the energy is greater than U0? I mean, I think it's pretty obvious that what happens here is, well, in general, all of these are no longer going to be these terms like that. Instead, I want to have a K1, or say this is K2 here in this region. I'll have a K1 and K3, which will be 2m E minus U0 over h bar squared. But this won't be, this will either be an exponential ikx or a sine or a cosine itself, right? So I'm going to have either plane waves or sines and cosines everywhere, okay? And in fact, I'm going to have plane waves everywhere, all right? So the particle is going to be racing around. And as I talked about last time, when you have, a potential that that has a well, you can either have a bound state, and a nice way to think about it is if your energy is less than the potential off at infinity, then you're going to be bound. If the energy is bigger than the potential off at infinity, then you have finite kinetic energy off at infinity, you're not bound. Okay, and so there's the notion of bound and unbound orbits. So if the energy is greater than u0, the particle will not get stuck here. And in fact, these are not the right waves to use. Cosine and sine is written that way, but rather I want to use the exponential form. So now I'm not going to treat that mathematically, although that's working that out is a perfectly good homework slash maybe pretty hard exam problem, but it, in some sense it would be completely fair game. But let's start with something easier. Let's just start with this. Well, let me make it a little bit smaller. Let's just put at x equals 0. Once again, this is energy. Let's put a potential u0. Here we'll have u equals 0. Here we have a potential u0. And we'll make the energy of the particle up here. All right. So I'm solving minus h bar squared over 2m. I'll use my new notation, psi dot prime prime plus u psi equals e psi. This will be region 1. This will be region 2. Just for giggles, I won't skip steps. Minus h bar squared over 2m psi prime prime 1 equals e psi. If I try a e to the I kx plus b e to the minus kx, and if I plug this in there, taking two derivatives down gives me h bar squared over 2m k squared, and I'm going to call this k1 equals e. All right? Just like we've been doing. A1 is the square root of 2m over h bar squared e. Okay? So that's psi in region 1. In region 2, I have minus h bar squared over 2m psi prime prime equals e minus u0 times psi, right? And the solutions in general could be c e to the I k2x plus d e to the minus I k2x. And if I plug this in and I take two derivatives, you see that I get minus h bar squared over 2m times I k2 squared. The negative sign goes away. I have k2 squared, and that's got to equal this. So k2 is 2m over h bar squared u0 minus c. All very straightforward. Just very straightforward. Okay? Now, but I do have to make some decisions. I chose to represent things with e to the ikx and e to the minus ikx. I did not choose to represent things with sines and cosines, though both will simply solve this equation, right? You can see that, right? If I just plugged in sines and cosines, they're going to solve the equation. Because I take two derivatives of sine or cosine, I get the negative sign out, it'll work. Why did I choose to represent it as e to the ikx? Can anyone think?
The energy is greater than naught.
So yeah, that's right. But I mean, I said I want the particles to be free, and the energy is greater, and I've argued that it's not bound. But so just mathematically, just mechanically, what happens if I pick cosine or sine? Remember that my full wave function, I write a capital psi here, is my space part, time is my time part, which I typically am not going to have to deal with. That's my space part, and my time part was, there's a constant which I'm going to ignore. It was e to the minus I omega t, right? So now if I chose a sine or a cosine, you know, I could have a cosine kx e to the minus I omega t. Just mathematically, what is that? It's just a bit of a, well, actually, do you know what this is? Do you remember the difference between a standing wave and a traveling wave? So that was one possibility. The other possibility was to take e to the I, let me write it as plus or minus kx, for the x part times the time part. I'll just combine, though, I just combine them, it's one combined numerator, right? So this was the one option if I chose the exponentials. This is the other option, or I could have had a sine if I chose sines or cosines. Mathematically, all of these will solve the wave equation. And in fact, right, of course, cosine can be written, if you remember, as cosine of theta is e to the I theta plus e to the minus I theta with a half in front. So this can be written as a combination of these things. But there's this basic idea in waves. If I represent a wave this way, this is something that in space is just a cosine. As time changes, that pattern doesn't change. It just sits there. It's cosine. There's a time part that modulates it. And so what it is this cosine wave that, well, the time part is actually just flipping around from being real to imaginary. So we think about just the real part. That's like a cosine. So it's just it's a wave that sits there in space, and then in time you're just changing the amplitude. It's maximal, and then it shrinks to 0, and then it flips negative, etc. This is a standing wave. Okay, if I set a string between two ends of the room, a rubber band, say, and I twang it, or just a guitar string, right? If you twang a guitar string, that's the description of the twanging guitar string, where I take the real part of this complex exponential. Okay? This is instead, as I talked about in detail, a traveling wave. It has that form, that magic form that I showed you. In fact, just the fact that it can be written as a function of kx minus omega t made it a wave. And this is, we talked a lot about this. One other reminder, so I'm going to pick I already did it. I picked the exponential. The other thing is, remember this business, this is either plus or minus kx minus omega t. So what happens if I pick plus kx? What is that? What is that?
Traveling to the right.
Yeah. If they have to have an opposite sign, the quick way to remember this, if these have an opposite sign, then as time increases and x increases, they compensate, you get the same mathematical value. Therefore, as time goes forward, x goes forward. If they have the same sign, as time goes forward, x has to go backwards. Right? A mean thing to do in an exam is to give you as a curveball that wave and say, is it traveling left or right? And often students will say, oh, well, it's positive k, it's traveling to the right. But no, if I stuck in a positive omega term, then that's a wave traveling actually to the left. All right? It was just important the relative sign of the x and the t. Okay? Okay, so this is a wave moving to the right. Let me just put a little r here. This is a wave moving to the left. This is a wave moving to the right. And this is a wave moving to the left. Okay? So now I also want to talk about the physical situation, and I'm out of time, so let me just say one thing. I can narrow it down a little bit more. I'm going to have waves coming in then from the left if I have the term A. So the way we'll talk about it is this is the incident wave. It's an incoming set of particles, if you will, from the left. They hit this barrier, and the wavelength, if you will, changes. It changes from the value of k1 to a lower value. Well, no, sorry, this is 1 over the wavelength. This is called the wave number sometimes. But k changes from whatever value it was to a lower value here, which is a longer wavelength. And you might remember from electricity and magnetism, if you have any wave, quantum mechanics, not quantum mechanics. If you change the wavelength due to a media change, so for the case of light, if index of refraction changes, you get reflection. It also would work if you had a mass on a string. If I have a guitar string across the room and I take two different strings and I tie them at the center, and then I pluck it at the end and I set a wave going down. When it hits the place where the density, where the string thickness changes, I'll get a transmission and a reflection, and that will happen, okay? So I should expect that I'll have this term, that's incident. This is going to be, let me label these, so I'm going to erase that. So this is incident. I'm just going to label these and then we'll quit. This is incident. That's reflected. This is transmitted. Okay? And I'm going to kill this term because that's a term moving to the left over in this region. And that's a perfectly valid mathematical term. It's a perfectly valid physical term. But when I want to talk about these problems, I've got to say, well, what problem am I talking about? And if I'm going to describe the A term as a wave coming in, possibly reflected, possibly transmitted, but look what I'm writing down. I'm writing down these waves which are over all space. Okay, so there's kind of like, I'm talking about a steady state phenomena of a flux of particles coming in from the left with some flux reflected and some flux transmitted, unless I put some sort of gremlin out there at infinity, also spitting back and reflecting particles. I simply don't want this in the problem I'm setting up. So I just choose to make that 0. So this is the initial starting point, and we're going to find A, B, and C and talk about them on Friday.